the previous video, we saw that for a very simple molecule, we needed to go from a molecular formula to a condensed formula in order to get our structure correct. Let's consider a more complicated example. Let's look at C6H14, which you may recognize from general chemistry is hexane. It's a saturated hydrocarbon. Because it has the general formula CN, H2N plus 2, which is the maximum number of hydrogens you can attach without having any double bonds. So there will be no pi bonds in this structure, C6H14, for hexane. And you probably remember that C5H12 is pentane, and C4H10 is butane, and C3H8 is propane, C2H6 is ethane, CH4 is methane. Up to propane, there's no ambiguity. Looking at the molecular formula, we can readily determine the actual structure. 3 carbons can only be connected like that without introducing unsaturation by forming a ring or putting a multiple bond, which would then allow us to attach the hydrogens as follows to create propane. 2 hydrogens on the middle carbon because it already has 2 other bonds to carbon, 3 hydrogens on each of the carbon on the end. We could write this as a condensed formula by writing CH3, CH2, CH3, which would tell us that these 3 hydrogens are attached to the carbon to their left. These 2 hydrogens are attached to the middle carbon, and these 3 attached to the carbon to their left. So in each case, the hydrogens are attached to the carbon written to their left, and the carbons are connected in order. For butane, though, we already have a problem. We already have a problem because you could connect 4 carbons in a linear fashion like that, but you could also connect 4 carbons by connecting 3 carbons to a central carbon. Once you have that skeleton, it would be a straightforward matter to put the rest of the hydrogens in. Hydrogens on each of the carbons that only has 1 bond to it, and 2 hydrogens on each of the carbons that have 2 bonds. Or in this case, 1 hydrogen on the carbon that already has 2 bonds, because we know that in the ordered form of filled on tech, carbon would like to have 4 bonds. Those 2 molecules are structurally different. They are in fact called structural isomers. Remember from general chemistry that the definition for structural isomers is that the atoms are connected in a different order. Structural isomers may also have been referred to as constitutional isomers. In chemistry, you would have learned that subsets of structural isomers are coordination sphere and linkage isomers. Where linkage isomers are the same ligand connected to a different donor atom in a ambidentate ligand, and coordination sphere isomers differed from one another by the presence of a ligand either inside the coordination sphere directly bound to the transition metal or outside the coordination sphere as a freely floating counterion. We won't be concerned with coordination sphere isomers in organic chemistry, and we won't in general call things linkage isomers. We had an example with the methyl cyanate and the methyl isocyanate. These two would not be considered linkage isomers. They're just plain old structural isomers. So we can draw those two different structures, and we can give them different names. And in fact, initially, this was known as N-butane, because it's normal butane. The N stands for normal, with a straight chain. And this one is isomer butane. So it's referred to as isobutane. Those are common names. They work well for the carbon-4 system, but they get a little bit more complicated with the larger chains where you get a larger number of possible isomers. It would be nice if we had a condensed formula that would allow us to distinguish between these two, rather than just writing C4H10 and then having to know the structure of N-butane and the structure of isobutane. And we can. In this case, these three hydrogens are attached to N carbons, so that's the CH3 group, a methyl group on the end. This is a CH2 in the middle, and the CH2 group is referred to as a methylene group. And now we have another CH2. Finally, the CH3. So a condensed form for N-butane would be CH3, CH2, CH2, CH3. Two methyl groups on the end and a pair of methylene groups in the center. Isobutane has two CH3 groups attached to that carbon. Actually has three CH3 groups attached to that carbon. And we can group those together, and we can write this as CH3, and then in parentheses, CH. That will tell us that all three of those CH3 groups are attached to the same carbon. And that's an isobutane. The CH group here is referred to as a methine. CH3 is abbreviated methyl, CH2 is abbreviated methylene, and CH is abbreviated methine. You could write a less condensed version by writing CH3, 2, CH, CH3. That would be legitimate. The one hydrogen in the center there is connected to the carbon that has three bonds to other carbons. These three hydrogens are attached to that carbon. Both of these CH3 groups that are inside the parentheses are attached to the carbon to their right, because there is no other carbon to their left. And these three hydrogens at the end are attached to the carbon in the middle. So we have two possible ways of writing C4H10 as condensed formula: CH3, CH2, CH2, CH3 for N-butane, and CH3,3CH for isobutane. Those are common names. The International Union of Pure and Applied Chemistry, or IUPAC, would simply refer to this as butane. And it would name this other molecule, isobutane, as a derivative of a three-carbon chain. The longest chain of carbons we see there is 3 carbons. So it is named as a propane, and then there is a CH3 group attached to the middle carbon. We would name this 2-methyl propane. Numbering the carbons 1, 2, and 3 going from left to right, we see that the methyl group is a branch on the 2-carbon, or 2-methyl propane. So this would be the International Union of Pure and Applied Chemistry name. Butane is the straight chain, 2-methyl propane is the IUPAC name for isobutane. Skipping over C5H12, let's go back to our original question, which is what structures can we draw for C6H14? How many isomeric hexane molecules will there be? So we can think about how to connect those carbons And there are several ways. One of which, of course, is to connect them all in a straight line, just like that. This would be N-hexane by the common name, N for normal, or just hexane in the IUPAC nomenclature. And then we would add our hydrogens, 3 on each end, 2 on each of the middle, so we have 4 methylene groups now in the middle, and 2 methyl groups on the end, and we can write this as a condensed formula by writing CH3, CH2, 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 CH3. That tells me that I can connect those in order, all the carbons connected in a straight line. But there are other ways we could connect those carbons. There could be a branch. We could, in fact, have connected one of those carbons to a carbon of a straight 5-carbon chain, and we could do it here at the second position, but we could also do it here at the third position. And those are 2 different structures that both have the formula C6H14 with a branch. And then we can connect our hydrogens. So it would be a combined group in each case. You'll notice that as I'm drawing these molecules, I am creating the carbon chain in a zigzag form. That reflects connected to 4 electron groups. And if each carbon is connected to 4 electron groups, it's a tetrahedral arrangement, which means that in fact, one of these hydrogens is coming out, and the other one is going back, and they're right on top of each other, and the angles are approximately 109.5. So I'm drawing the zigzag to make those angles look more approximately like they really are. Here, I haven't really done that. And the reason why will become clear shortly. As you can see, when we start getting these larger molecules, it becomes a little bit of a pain in the neck to draw full Lewis structures with all the bonds. And we have a solution to that problem as well, called bond line formulas, which we'll get to in just a second. But first, let's think about how we can write these as a condensed formula that would allow us to distinguish between the 2. This one would be called 2-methylpentane. And this one would be called 3-methylpentane. Reflecting the fact that each of those has a longest chain of 5 carbons, but on the top structure, the CH3 group comes off the second carbon, and in the bottom structure, the CH3 group comes off the third carbon. To draw this as a condensed formula, we would recognize that for the 2-methylpentane, we actually have 2 CH3 groups attached to the same CH, and then we have CH2, and CH3. For 3-methylpentane, we have a CH3, and then we have a CH2, and then we have a carbon that's attached to hydrogen and a CH3. We'll put that CH3 group that's coming down off the bottom here in parentheses to indicate that we know that the entire contents of that parentheses is attached to the carbon to its left. These 3 hydrogens are attached to the carbon to their left within the parentheses, but then the parenthetical carbon is connected to the carbon to the left of the parentheses. And then we'll have a CH2. So we can readily distinguish, using a condensed formula, between 2-methylpentane and 3-methylpentane, which are 2 isomers of hexane. To draw a 4-carbon chain, and then have the other 2 carbons branching off that chain. And they could either be branching off different carbons, so we have a methyl group on both carbon 2 and carbon 3. This molecule will be known as 2,3-dimethyl butane. by connecting 3 hydrogens to each of the carbons that have only one bond. 2 hydrogens to each of the carbons that has 2 bonds. And 1 hydrogen to each of the carbons that has 3 other bonds coming from it. This one is a quaternary carbon. That carbon already has 4 bonds, so we won't connect any hydrogens to it at all. Now you will need to lengthen that bond a little bit. There's room to draw all of them. And I don't know about you like this, because it seems a little annoying and repetitive to keep writing all of those hydrogens in. Condensed formulas are one solution, and we can distinguish these 2 condensed formulas, 2,3-dimethylbutane, 2CH, CH, CH3, 2 CH3 groups attached to it, and 2,2-dimethylbutane would be written CH3, 3C, CH2, CH3, representing the fact that all 3 of these CH3 groups are attached to that given carbon. So condensed formulas allow us to distinguish between N-hexane, 2-methylpentane and 3-methylpentane, and 2,3-dimethylbutane and 2,2-dimethylbutane, which are the other possible structures. 2-methylpentane is also referred to as isohexane. It is an isomer of hexane that has a branch point in the same location as isobutane. But then 3-methylpentane doesn't really have an obvious name, or also don't have obvious names. So how could we draw these in a simpler manner where we can see the overall structure of the molecule without writing in all the hydrogens? And the answer is we're going to do a shorthand called a bond line formula. But instead of writing the carbon atom, just writes the bonds. It's understood that every point that has lines emanating from it is a carbon. So this is a carbon with 1 bond, 1 line emanating from it. This is a carbon that has 2 lines. This point here is a carbon with 2 lines, another point, and then this point on the end is a carbon. So there are 6 points, 1, 2, 3, 4, 5, 6, each of which represents a carbon, and then we don't draw the hydrogens. It's understood that there are enough hydrogens attached to fill a valence of 4 and create 4 bonds to each carbon. So each point from which only 1 line emanates is understood to have 3 hydrogens attached. Each carbon from which each point from which 2 lines emanates is understood to be a carbon that has 2 additional hydrogens. And when we draw a bond line formula for this, that carbon has 3 lines emanating from it. It's understood that it has just 1 hydrogen on it, which is all it needs to fill its valence. The bond line formula for 3-methylpentane would look like this. That's a much more convenient shorthand method for drawing these isomers that doesn't require drawing all the bonds or writing the symbols for all the atoms. And you can't get the number of hydrogens wrong because it's understood that you know there's only 1 hydrogen attached there. Even if you think there are 2 hydrogens attached there, I won't know you think there are 2 hydrogens attached there. I'll assume you know what you're doing. 2,3-dimethylbutane would be written like this. And 2,2-dimethylbutane would be written like this. So those 5 skeletons are quickly and easily drawn as bond line formulas without writing any carbons and without writing any hydrogens. If a point is some atom that isn't carbon, then you would write the symbol. So if rather than having a hydrogen here, you had OH, you would actually write the oxygen there, indicating that you know that that point is in fact an oxygen. And it's sometimes not necessary to write the bond to hydrogen. We show the OH group as a condensed formula. So you can mix condensed formulas and long line formulas in some cases when you want to focus on the actual structure of one of the substituents without focusing on all the atoms present in the other parts of the molecule. In practice, most of the molecules that you see drawn, if you go to Wikipedia and look up a drug compound, they will usually be written in a bond-line formula with some portions of the molecule singled out and written as condensed forms. You will very seldom actually see a full Lewis structure written when you're looking at more complicated molecules in organic chemistry. So we'll have to become familiar with drawing our molecules as either bond-line formulas or as condensed formulas. Some structures are particularly common. This molecule is referred to as benzaldehyde. This carbon double bond oxygen, two lone pairs on the oxygen, attached to a hydrogen is the aldehyde functional group. And this group out here is mostly a benzene ring. Benzene itself is a six-membered ring with alternating single and double bonds. And it's understood that there's a hydrogen attached to fill the fourth bond and make each carbon have four things attached to it. Benzene is C6H6. And when you see C6H6, generally it's benzene and it's put together like this. But you'll notice that we're not writing the carbon atom. It's understood that each of those things is the carbon atom. This group here is often abbreviated C6H5. And when you see C6H5, it's understood that the structure looks like that. It's also referred to as a phenyl group. And the phenyl group has abbreviations PH and occasionally just the Greek letter phi. So C6H5, phenyl, PH, and phi are all shortcuts that represent this six-membered ring, a regular hexagon, with carbons separated from each other by alternating single and double bonds. It's written CHO. The hydrogen and the oxygen are both connected to the carbon. Right? It's understood that this hydrogen is not attached to the oxygen, but to the carbon, because it's always attached to whatever the atom to its left represents. And then it's understood that there's a double bond between the oxygen and the carbon, because that would be the only way of filling the octet on carbon. So benzaldehyde can be written in condensed form as C6H5CHO. And it can be written in bond line form like this. I don't actually even need to show the carbon. It would be appropriate to leave that carbon off. Four bonds emanating from it, two to oxygen and one each. When you're writing an aldehyde, it is conventional to draw the hydrogen of the aldehyde rather than leaving it as just a kind of terminal angle like that. So when you see a CHO in your condensed formula, you'll know that represents an aldehyde. When you see CO2H, you'll know that that represents carboxylic acid. So one condensed form that I could write would look like that, H3C, C6. In this case, the hydrogen is written to the left of the carbon. They have to be attached to that carbon because there's nothing else to their left, and they can't be attached to each other. The C6H4 group represents a benzene ring, and then we have a CO2H. The CO2H group is understood be a carboxylic acid function. You'll note that in this case, the hydrogen is written to the right of the oxygens, which indicates that it's attached to oxygen, not to carbon. And then the only way to fill that octet on carbon is to double bond the other oxygen. Otherwise, you wouldn't have a fill octet. And on this side, we have the CH3. That's kind of a hybrid between a condensed formula, right? On this side, I write H3C for the condensed form, a line structure for the middle, the C6H4 part, and then a full Lewis structure with lone pairs on the end. I could draw that same molecule without showing CH3 just by leaving it as a terminal line. Understood that that's carbon, and since it would need 3 hydrogens to fill its octet, it has 3, and I don't need to actually show bonds, or I don't have to write the carbon, right? It's understood that that's a carbon because I have to label it something else, and in this case, I've now taken that OH group and made it a condensed form. Those are both reasonable structures for 4-methyl benzoic acid. And I have to say 4-methyl benzoic acid to indicate that the CH3 group is attached opposite the COOH group in the 4 position. This isn't actually enough to tell me that it's 4-methyl benzoic acid. That condensed form could equally well have been 3-methyl benzoic acid or 2-methyl benzoic acid. Those both have the same structure. So 3-methyl and 2-methyl benzoic acid have the same condensed forms, H3C, C6H4CO2H. So I would actually have to specify that this would be the 4 position by putting a 4 in front of the condensed formula. So you'll see that C6H5 often for this group here. It's a benzene ring with one thing attached to it. You'll see the benzene ring abbreviated as C6H4 when it's in between 2 things. And you'll understand that that's not a saturated hydrocarbon anymore. It's no longer CnH2n plus 2. It has degrees of unsaturation introduced by double bonds. Each time you put a double bond, you take 2 hydrogens away, or a ring. Okay? And we'll have much more to say about unsaturation and degrees of unsaturation in the future. So bond line formulas and condensed formulas are useful ways to look at molecules in organic chemistry, and you'll need to get comfortable with switching back and forth between bond line formulas and condensed formulas. And in all cases, of course, it should be possible for you to write a full Lewis structure if you wanted to, but you'll very seldom actually want to. So let's look at an example. Let's consider CH3, Q, CH, CH, OH, CH2, CH2, CHO. That's a condensed form. How would we convert that into a bond line form? So we have a carbon here that's attached to 2 methyl groups. And then the next carbon would change. So there's a CH3 group, carbon, 1 point, needs 3 more hydrogens. There's another single point, needs 3 more hydrogens. This carbon has 1 hydrogen on it, 3 bonds. Then there's a CH, and it has an OH group hanging off it. And then a CH2, and another CH2, and then the CHO group is our aldehyde. So this would look like that. 1, 2, 3, 4, 5, 6, 7 total carbons. 1, 2, 3, 4, 5, 6, 7. The end carbon is attached to a double bond to 1 oxygen and a single bond to a hydrogen. This OH group in parentheses, the entire group is attached to the carbon to its left. And then 2 CH3 groups attached to the initial carbon. To name this this compound, we would start numbering at the most highly oxidized carbon, which is the aldehyde A. The longest chain we can have is 6 carbons. So the base molecule here is a hexanal. We've taken off the E ending for hexane and replaced it with Al for the aldehyde. And then attached to that, we have a hydroxy group. And we have a methyl group. We're going to put in front of the hexanal the location of each group, and we're going to put the groups in order by alphabet. So hydroxy, because it starts with H, comes before methyl, and this would be written as 4-hydroxy, 5-methyl, hexanal. You'll notice it's not necessary to specify that the aldehyde is a carbon 1. It has to be a carbon 1 because the aldehyde functional group has a carbon attached doubly to an oxygen, singly to a hydrogen. That can only happen if it's a PA. 4-hydroxy 5-methyl hexanal, you'll notice that the numbers are set apart from the letters in the structure by dashes. You'll notice in the previous example where we have the 2,2-dimethyl now, the numbers are separated from each other by commas. 2,2-dimethyl butane, the numbers separated from each other by commas and from the letters by dashes. And this molecule would be 4-hydroxy 5-methyl hexanal. There's lots of practice problems. You'll get